soon. Also, as I reminded you previously, in order to catch up, this audio sound all right? Sounds funny to me. Sounds echoey. Aha. Now it should be better. That mic was on also. I will select some videos from 46 classes that I've already conducted and instruct you to view these things so that we can get at all the material we need to get at this term to make the course complete. As I reminded you, UF administration can't even count calendar days. They don't recognize we don't have the same number of class days in the spring as we do in fall. Or put another way, we are short of class days in the fall. If they'd simply extend the term one further week into December, we'd have no trouble. But they don't want to interfere with holidays. I mean, after all, 5 weeks off isn't enough. I mean it, folks. This is a great time of life to get something which you will be using for your entire life. It's called education. And anything that shortchanges that is not what the hell a university is supposed to do. At least not as I see it. In any case, I will of course tell you what these videos are as soon as I determine them. Then I will identify them by number and date and topic. Some of that will relate to the topic we will start in just a few moments, Electrochemistry, Chapter 22. Now then, to finish what we were at the conclusion of our last gathering, which is wrap-up of Chapter 21, and considerations regarding Ka for HCl. Before we tackled the computation, we knew if the acid strength order in our acid-base table is correct, KaHCl has got to be bigger than that for nitric and smaller than that for sulfuric. Calculation of KaHCl is simple. You write HCl gas, because it's gas under normal lab conditions. The conditions for which the data are tabulated in Table 1 at the end of Chapter 20, the thermodynamic properties table. So you're looking at HCl gas plus water liquid, equilibrium with hydronium ion AQ and chloride ion AQ. So we go to Table 1. Specifically, we're looking for delta G sub F super 0 data so that we can get delta G 0 for this reaction, from which we can calculate K, which in this case would be Ka for HCl. Don't need delta G sub F super 0 for water and hydronium ion, because delta G sub F super 0 for hydronium ion is equal to that for water liquid. So when you look up delta G sub F super 0 for chloride ion aqueous and subtract from it delta G sub F super 0 for HCl gas, the pure stuff, you get delta G 0 for the reaction, from which you get K, which is 2.0 times 10 to the 6th. And then, as we have reminded ourselves, which of course was part of quiz 3, if you need units for an equilibrium constant that you've calculated from thermodynamic data, given that by rigorous definition equilibrium constants are unitless, the only way to get the units, should you need them, is to look at the equation for the reaction. The equation for the HCl ionization reaction with water shows you that the units are m squared for moles per liter in the numerator per atmosphere. Goofy units. So if we wish to get the equilibrium molarity of HCl in the solution, we've got to do some unit conversion. Because again, just for fun, we're interested in convincing ourselves that since this Ka value is very large, there will be, practically speaking, no HCl remaining in solution. But the equilibrium constant as written reflects the partial pressure of HCl over the solution. Because again, at NLC, HCl is a gas. Well, we also know that HCl is quite soluble in water. Because it reacts with water, obviously. And if for no other reason, it's a polar material. And water is a polar solvent. So how can we relate this expression to this expression where HCl at a partial pressure of 1 atmosphere over the solution is expected to dissolve entirely to give us what initial molarity of HCl? Because we're starting at standard state conditions. This is initially 1 molar, this is initially 1 molar, and this is initially 1 atmosphere above the solution. So what initial molarity of HCl will be equivalent to initial partial pressure of HCl gas at 1 atmosphere? Well, to make the matter as straightforward as possible, we'll assume that HCl's gas behavior as a gas is describable by PV equals nRT. So we'll take PV equals nRT and rearrange it as a ratio of moles per volume. Because if volume is in liters, this is molarity. So we put in the partial pressure of HCl, here's the R value, there's the T value at NLC, we get 0.041 molar. Nothing fancy about this. So now we can equate this expression to this expression by writing the initial molar concentration of equivalent of partial pressure of HCl gas at 1 atmosphere as 0.041 molar. So the equilibrium molarities, since this reaction, well, we haven't written the reaction, HCl gas plus water, double arrows, hydronium ion, chloride ion, aqueous, with a K value like that, we're knowing that reaction goes very much left to right as written to get us to equilibrium. And the stoichiometry says the resulting molarities of hydronium ion and chloride ion will be equal. So we'll write them as this. And the equilibrium molarity of HCl, after having started with 0.041 moles per liter concentration, will be this. At a glance we can see with this huge K value. You don't even have to operate on this arithmetically, practically speaking, to see the answer. This has got to go almost to nothing, which means this has got to go to about 1.041, because all of this is going to become this, practically speaking. Of course, you can't take it to be absolutely converted, because then the equilibrium constant disappears, becomes infinity. So if you stretch out this calculation until you can find a non-zero significant figure for the resulting equilibrium molarity of HCl, you'll get this. 2.2 times 10 to the minus 8 molar. I think it's pretty fair to say then that the HCl originally dissolved has reacted, practically speaking, 100%. And if you want to do the corresponding equilibrium partial pressure calculation of HCl, it'll be this. But this really is meaningless, because there won't be any HCl vapor above this solution. It'll all be dissolved. So I'll put quotes on this. Just as a way of showing you how you can extract all kind of meaningful, significant chemical information from the thermodynamic properties data table. Again, our pursuit at this stage of the game for Chapter 21 considerations was to show you how the thermodynamic properties data table can be used to get Ka values for very strong acids. All right, challenge problem 21-2. Again, we're talking about a couple of the selected challenge problems from the end of Chapter 21. Theoretical chemists today are still wrestling with the issue of what is the true nature of the hydrated H+ species. At the minimum, it's hydronium ion. At the minimum, because of the enormous positive charge density of H+. H+ has got to be associated with at least one water molecule. Well, theoretical chemists have said, well, my golly, with this enormous positive charge density, can we imagine that H+ associates with more than one water molecule? If you think about it from a basketball's BB's relationship, since to a single BB we can glue 2 basketballs but not more, on that basis H5O2 plus is reasonable speculation. Here's our little dot H plus and one water molecule on each side of H plus. But I don't see any way you could snuggle another water molecule into direct contact with the dot proton while at the same time not having the water molecules sterically interact with each other and block each other from contact with H plus. So at the minimum, I would argue with theoretical chemists, I don't give a damn what you do with your calculators and your computers and your fancy arithmetic. Going past H5O2 plus makes no sense, at least not to me. Now then, let's go back to the end of Chapter 19. You remember at the end of Chapter 19 we introduced ourselves to Lewis acid, Lewis base chemistry? Because when H plus interacts with water, H plus is behaving as a Lewis acid, not just a Bronsted acid. And water is behaving as a Lewis base, not just a Bronsted base. You remember how Lewis acid is defined? It's a species with one or more empty valence orbitals. Remember that? How many empty valence orbitals does H plus have? I mean, this is very fundamental atomic structure stuff, which all comes from the theoretical people. How many empty valence orbitals does H plus have? 1, that's it. So how many coordinate covalent bonds can it make? 1, that's it. So when the water molecule interacts with H plus, creating hydronium ion, you have saturated the empty valence orbital which H plus has. It only has 1, so I'm telling the theoretical chemist you can do whatever the hell you want with your fancy calculators, because my horse sense chemistry tells me hydronium ion is right, and you can take and shove all the rest of this stuff. You think I have an attitude about this? You're damn right. It strikes me when you let common sense escape or go away, you got a problem. I'll tell you a story relating to this. Have you ever seen the old game show? I don't know that it's on anymore. With Monty Hall, Let's Make a Deal. 3 doors. Remember that? You're looking at 3 doors. You don't know what's behind each door. The player, the contestant, is asked to select one of the doors. Door 1, door 2, door 3. Well, initially then, what are your chances of picking the door behind which the pot of gold stands? 1 out of 3, right? Nothing fancy about this. So let's imagine contestant picks door 1. And then Monty Hall says, I will now show you that behind door 2 is not the pot of gold. So he opens door 2, there's no pot of gold. And he says, now you can do one of 2 things. keep your door 1 selection or switch it to door 3. That's it. What should you do? Should you keep the door 1 selection or switch to door 3? Switch. Why?
Because your odds are better.
What are the odds now?
1/2.
That's right, 1 out of 2. Isn't that nice? Originally your odds are 1 out of 3. Now you've increased the odds of winning to 1 out of 2. You better switch. And mathematicians played with this damn thing for a long time, doing all kinds of fancy calculations because they refuse to let common sense tell them what the hell the answer is. Want to make it real obvious? Let's take a pack of cards. 52 cards in the pack, right? I'm thinking of a card. What are your chances of picking the card which I think from the original pack? 1 out of 52. Okay? Now then, you write down your choice, the card you think I thought of. Queen of diamonds, 4 of clubs, who gives a damn? Okay? Now I'm going to show you 50 cards showing you that in the 50 cards that in the 50 cards which I now show you, the card I'm thinking of isn't there. I throw those cards away. So I now have 1 card which you picked originally out of the 52. Where your chances of telling me the right card is 1 out of 52, or the other card. Should you switch? If that doesn't make it obvious, I don't know what can. What are your chances of winning now? Don't tell me 1 out of 2. Remember, originally your chances of winning was 1 out of 52, right? What's your chances of winning now? Try 51 out of 52. Pretty good, huh? Because it's a good bet that first card you picked wasn't the right card. Right? And I threw away 50. That leaves 1 card. You better pick that card. You've increased your odds of winning from 1 out of 52 to 51 out of 52. Pretty good chance. You see how the 2 possibilities add up to 1? 1 out of 52 added to 51 out of 52 gives you 52 out of 52. Because if I let you pick the whole pack, you got to get the card. That's it. So I'm taking this, and they can burn their computers. On we go. Problem 21.3 says, this is nothing but an arithmetic question. You remember, if delta GR equals 0, then delta HR0 equals T delta SR. You were asked to think about this yesterday. Nothing fancy about this. And this condition corresponds to, if you got an equilibrium involving gases, an equilibrium constant expression which is equal to what value? Well, it really doesn't have to involve gases. If delta G0 equals 0, the system is at equilibrium under standard state conditions. What's the value for the equilibrium constant? 1. Well, problem 21.3 says, what if I make the value for the equilibrium constant 1.0 times 10 to the minus 3? For whatever the equilibrium is. How do I calculate the temperature at which this reaction has an equilibrium constant value of that? There's nothing to this. Here's what you consider. This is now K. So put it in. Take the log, it's minus 3.00, okay? And use this equals to this, with this being equal to minus 3.00. Now delta HR 0 and delta SR 0 are taken as isothermal values. You get the isothermal values, you get them from table 1. So what do you got? An expression with how many unknowns? If you know this, and you know this, and this is a constant, the only thing in here unknown is T, isn't it? So can you calculate T when log K is minus 3? Hell yes, done. So we go on. Finally getting to electrochemistry. By definition, the qualitative and quantitative study of redox reactions. Redox reactions, by definition, are reactions in which atomic oxidation numbers change. Redox reactions are arguably the most important subcategory of chemical reactions, or category. Because not only are most reactions redox, most reactions of consequence with respect to energy liberation are redox. Like the reactions which take place in our system that allow us to derive people energy from food energy. So that I have consistent strength to take this wonderful device and shove it across the board and write things on the board which interest you greatly, right? Strength which allows me to stand here before you and as I see fit to tell the administration of UF that they are really stupid in many areas. Last week I received from UF, the administration of CLAS, College of Liberal Arts and Sciences, an outline of this great strategic plan to make things better. If I understand this plan correctly, it took them 3 years to develop this. The plan is loaded with flowery statements, all of which leading to improving the quality of research and improving the quality of undergraduate education. This is fine and dandy. There's only one part missing. There are 0 details in this plan which indicate how these things will be accomplished. Wonderful. Anybody can sit down and write a great mission statement, but how many can sit down and show you this is how you're going to accomplish this mission? That's where the doing is done. It's in the details. It's in the dirty work. Now, if anybody does this dirty work, who do you think it's going to be? The administration? It's going to be people like the one who's telling you about this right now, at least as far as the undergraduate education part is concerned. And I'm all for it. But I'm going to respond to this because the College of Liberal Arts and Sciences asked me to respond. And I'm going to say, why is it that since I've been part of this faculty since 1987, not once has this administration ever invited me to sit down and discuss with it how we can go about improving undergraduate education? Yet that's my life. That's what I do. And not once have you even asked me about how this might be done better. But on many occasions you've issued dictates which require me to act in ways which I consider to be standing in the way of improving undergraduate education, and in fact making it worse. I mean, if this is their idea about how to improve undergraduate education, all I can say is I don't share it. Interesting, isn't it? I'm also curious, how many other faculty with whom you've had classes talk to you like this? You see, I'm a person, I have feelings, and I want you to know what these feelings are, especially when they're important to what the hell's going on at this place called the University of Florida. So I don't mind sharing this stuff with you. Could I be wrong? You're damn right. I don't claim to have any crystal ball, but I do claim to try to approach problems with common sense, like I just told you about the Monty Hall deal and hydronium ion and stuff like that. And until you can come after me with a superior argument, I'm sticking to what I got. On we go. What we're now interested in is, at the start of our conversation on electrochemistry, is to come to grips with the best way to determine oxidation numbers. Atomic oxidation numbers. You did this in Chemistry 2045 because it's a part of the nomenclature game. Were you reminded in 2045 that oxidation number assignments all depend on electronegativity? That's where they all come from. And oxidation numbers are important. They're important for electron bookkeeping. They're important for assisting us to write equations for reactions, in particular redox reactions, which is what we are now about to tackle. Because just like with acid-base chemistry, we had to learn to write equations for reactions, which before we could go about the business of quantitatively analyzing any acid-base system. Because if you don't know what the hell chemistry is going on in the system, how can you possibly tackle this problem? Same thing with electrochemistry. We've got to learn to be able to write equations for redox reactions before we can tackle the chemistry of the system. And this is not easy. It's not easy. So I ask you, bear with me. Do what I tell you to do, as I've always told you. Beginning today, if we get to it, or the next class for sure, we're going to start to take a look at all the rules of the road for developing equations for redox reactions, which are in Chapter 22 notes. You think I expect you to read this and think about it and pay attention to it? Do I have to say this? Because without your attention paid to this, you can't achieve this. It's too damn tough. And guess what you're going to find these rules depend heavily on? Would you be surprised to find that they depend heavily on acid-base chemistry? I hope not. Would you be surprised to find they depend heavily on reactions which involve the formation of salts of limited solubility in water, like Chapter 19 stuff? Would you be surprised to find that these reactions depend heavily on formation of complex ions? End of Chapter 19 stuff? How about that? You see, we're taking advantage of what presumably we've learned so we can go to another level. You forget what we already paid attention to? You might as well go away now. You have no chance. But if you keep in mind what we've already paid attention to, then you're ready to go. All right, on with this oxidation number stuff. Couple species. By rules of the road, stuff that you learned in 2045, you've recognized, I should think, that in just about all compounds which contain oxygen, oxygen exists in what oxidation state? -2 or 2-. But sometimes -1, as in peroxides. On rare occasion, -0.5, as in superoxides. And on one extremely rare occasion, a positive oxidation state. You ever seen a molecule which contains oxygen in a positive oxidation state? If oxygen is going to exist in a positive oxidation state, to what element must oxygen be bound? Fluorine. Fluorine is the only thing more electronegative than oxygen. There's the molecule. What's the oxidation state for oxygen in this stuff? What is it? What is oxygen oxidation state in this stuff? +2. How about that? Now then, let's show you the best way to get at this stuff. Nitrate ion. Before we even do this, I expect that you know that the only Lewis structure you can write for nitrate ion, which meets with the rules of the road, is this. It shows these two oxygen atoms in -1 formal charges. Don't get formal charges confused with oxidation states. They're not the same thing. The central nitrogen atom, formal charge of +1. The so-called doubly bonded oxygen, formal charge 0. The whole thing adds up then to a total formal charge of -1, which corresponds to the -1 charge on nitrate ion. You know this stuff. You also know that this is not a correct representation of the valence electron structure of nitrate ion, right? Because there are no NO single bonds or an NO double bond in this species. This is a resonance stabilized species. Every NO bond is the same length and strength. Every one is shorter and stronger than NO single bond, longer and weaker than NO double bond. The bond order is 4/3. Every NO bond, the NO bonds are equivalent. They're all the same, length and strength. But back to the oxidation state business. After you write the Lewis structure, to get oxidation states determined, or oxidation numbers, whichever you wish to call them, you go to each bond site. That's all you have to do is focus on the bond sites. And parcel the electrons in favor of the more electronegative atom. So you do need to know about atomic electronegativities. Remember, it's a lot of fun to know about electronegativities, isn't it? There it is. The electrons are parceled, given that oxygen is more electronegative than nitrogen. And now after parceling the electrons, you apply this recipe, where O in capital O in parentheses means oxidation state or oxidation number. You take the number of valence electrons for the isolated atom. That comes from the periodic table. What's the number of valence electrons for an oxygen atom all by itself? What? 6. It's in family 6A, isn't it? And for the atom in question, after you determine the number of electrons it has as an isolated atom, using the periodic table, you look at the Lewis structure after you've parceled the electrons and you subtract from that valence electron count, the one you got from the PT, the number of electrons which the atom has in the Lewis structure after parceling. 1, 2, 3, 4, 5, 6, 7, 8. All the same. 1, 2, 3, 4, 5, 1, 2, 3, 4, every one. So every oxygen atom is -2. Oxidation state of every oxygen atom in this is -2. How about nitrogen? Well, how many valence electrons? Nitrogen all by itself? 5. How many valence electrons for nitrogen after parceling? None. 5 minus 0. Oxidation state nitrogen plus 5. And if you add up all the oxidation states, it's like summing all the formal charges. You'll get the charge on the species. You have to. Plus 5 minus 2 minus 2 minus 2. Total is -6. Plus 5 added to -6 gives -1. All done. Now let's try something a little bit more challenging. The acetic acid molecule. Best typed formula. But watch out for this type formula for the acetic acid molecule, because it tends to lie. Because in the acetic acid molecule, are there or are there not oxygen to oxygen bonds? There are none. Lewis structure, acetic acid molecule, on your paper right now. Do it. How many got this? Now, another consideration regarding oxidation numbers, which I've seen in textbooks, which is grossly misleading, is to calculate the average oxidation numbers for the carbon atoms in the acetic acid molecule. Who gives a damn about average oxidation numbers? It's like students who keep on asking me, what's the average for the class? There's nobody in here named average. It doesn't mean anything. I've told you time and again, each student in this gathering gets a score, a grade if you wish, as if he or she is the only student in the class. It makes no difference what the other people have done. None. As far as your grade as an individual is concerned. So why do you ask me about averages? It doesn't mean a thing. You want a true average, I have to give you an average for every student who's taken this class from me in all the many years gone by when I've covered the same material, which is just about all the time. Then you'd have an average which is reflective of average. But it still wouldn't mean anything. Believe me. If you have a class of 1,000 students, and 500 are hard chargers and all work hard and earn an A, and the other 500 don't give a damn, they think the university owes them a degree for showing up. Well, you might get away with that in some classes, but you're not getting away with that stuff in my class. So I got 500 A's and 500 flunks. What the hell does an average mean? What does it mean? It doesn't mean anything. Not a thing. As far as I'm concerned, you got 500 university students and 500 people who need to be kicked in the butt right out of here. Gone, get away. You got no business being here because you're not here for an education. If you're not here for an education, get out. You don't belong here. You're taking up space that somebody else should have. Okay? Let's go to each bond site. How does the electronegativity of hydrogen compare to carbon? Which is more electronegative? Carbon. Keep in mind, if you didn't remember this. I think I told you this, but if not. Since so many molecules are composed or contain oxygen, nitrogen, carbon, and hydrogen. You believe that? You don't believe it now, wait till you go to organic class. You'll believe it then. It's valuable to remember the electronegativities of the atoms of period 2, because these three very important atoms, oxygen, carbon, and nitrogen, are members of period 2. So we'll start with fluorine, which has the highest oxidation number value of 4.0. Other scales, different values. Who cares? We'll take the easy one, the Pauling scale. 4.0, and as you march from right to left and come from atom to atom between neighboring atoms, there's a difference in electronegativity of 0.5. That's it. You probably heard this before. Oxygen 3.5, nitrogen 3.0, carbon 2.5, boron 2.0, and when you get all the way to lithium, you got 1.0, and so this leaves you with one more atom whose electronegativity you should remember. What is this atom? Hydrogen. Electronegativity is 2.1. Bingo. So now, in what we just said about the period 2 atoms, we've told you the only nonmetal atom which arguably has a lower electronegativity than hydrogen. What is this nonmetal atom? The only nonmetal atom which has a lower electronegativity than hydrogen. What is this atom? Boron. 2.0. Bingo. In any case, that's all we need to get at the parceling business. Now then, when I have covalent bonds between like atoms, how shall I parcel the electrons? Equally. Divide the number of electrons at the bond site in 2. That's all there is to it. So let me extend this bond a little bit, and I'm going to do this to it. I chopped it in half. Okay? So here we go. You know the hydrogens are all +1, the oxygens -2. So let's get at the carbon atoms. Those are the atoms whose oxidation numbers are of interest for this analysis, because those are the atoms who have oxidation numbers which we wouldn't know straight away. All right? Carbon by itself. How many valence electrons? This carbon. 2, 4, 6, 7. So this carbon's -3. Now then. 1, 2, 3, 4 plus 1 hydrogens, -2, -4. So the sum of the oxidation numbers for the non-carbon atoms in this thing is equal to 0. That tells you this carbon has got to have what oxidation number? What has it got to be? +3. Let's see if it is. 4 -1. How about that? Now you think this information might be useful when you're studying organic chemistry? Do you remember at the end of chapter 19, we mentioned in brief electrophiles and nucleophiles. Maybe we didn't mention them, I don't know. And a Lewis acid. A Lewis acid is an electrophile. What's phile mean? P-H-I-L-E. What's it mean? Love. Electro. Call it electron. An electrophile is electron loving. Nucleophile. What's nucleo stand for? Nucleus. What kind of charges do we find in the nucleus? Positive. So a nucleophile is something that's rich in electron density and it's looking for something plus. Ain't that right, Coulomb? Ha see, that's all there is to it. So you now recognize if this molecule engages in reactions which involve the carbon atoms and it's attacked by an electrophile, the electrophile will attack which of these carbon atoms? This one or this one? If this molecule engages in chemistry involving its carbon atoms and is attacked by a nucleophile, which carbon atom will be attacked? This carbon or this carbon? The nucleophile hits which carbon? The -3 carbon or the +3 carbon? This one. This is the one that's plus, isn't it? The nucleophile, looking for a nucleus, looking for something that's plus. The electrophile, looking for something that's electron rich. Bingo! How about that? You already know something about organic mechanisms from this simple analysis. Now then, I want you all to tackle this question number 22 on histidine. Not 22, pardon me. It's question 2 in chapter 22. Histidine is an amino acid. You've developed any familiarity with amino acids this term? How about that? Amino acids important? We wouldn't be here talking about this stuff without amino acids. An integral part of human chemistry, okay? Look up this amino acid, look up its structure, it's easy to find on Wikipedia or whatever the hell, and parcel electrons so that you can respond to this question. We'll pick it up from this point next time.